In this video, we'll go over the basics of convergence, completeness, and power series in the complex numbers. First, let's talk about the basics of convergence of complex numbers. Convergence works just as it does with the real numbers or R2. So a sequence of complex numbers written this way, where n runs from 1 to infinity, converges if there's a complex number such that for every epsilon there exists a natural number such that an minus L is less than epsilon for all big enough n. So this is the usual epsilon and n definition of convergence of sequences. And when this happens, we write that the limit of the sequence is L, or we might write something like an goes to L as n goes to infinity. Using this basic definition, you can establish, just as you would in a real analysis course, a bunch of basic limit rules. So here, assuming all of these quantities exist, you can prove that the limit of a sum is the sum of the limits. The limit of a product of complex numbers is the product of the limits, assuming both limits exist. You can take the limit of a quotient as the quotient of the limits as long as the bottom limit is non-zero. And here you'd have a little trouble if you had a bunch of bn's that were zero, but as long as the limit of the bn's is non-zero, eventually all of the bn's will be non-zero and you can make sense of this. And finally, a limit of complex numbers exists if and only if the real and imaginary limits exist, and that's just corresponding to how convergence would work in R2. You have a sequence in R2 exists only if the limit of the individual components exist. Now here's a basic but important example. Let's take a complex number z less than 1 and consider the limit of z to the n. So the limit of z to the n as n goes to infinity will be 0 because the modulus of z to the n is just modulus of z to the n, and so this will be a number less than 1, and we know from calculus or real analysis that this would go to 0. Of course, when z equals 1, this limit is just going to be 1 because all the numbers are 1. And you can show that for all other cases, so for either z on the unit circle except for 1, or for z with modulus bigger than 1, this sequence does not converge, and here's kind of a short way to show that it can't. So if it did converge, say the zn's converge to some L, then shifting the sequence zn plus 1 will still go to L. But you're multiplying the sequence by a constant, and using the basic limit rules from before, a limit of a bunch of constants is just the constant, and so this would go to ZL. So you get that either, if this limit exists, it has to equal L, or you have to have Z equal to 1. And we can't have the limit equal to 0 if all of the numbers are greater than or equal to 1 in modulus. So this is a way of just showing that the limit won't exist in all other cases. Next, let's talk about convergence of series or infinite sums. So a series is just going to be our name for an infinite sum. And initially, this can just be a formal object where we don't have to talk about its convergence or not. It's just a notation that we want to sum it in some fashion. And our first notion of convergence will be that a series converges if the partial sum sequence, which just means you form a sequence by taking partial sums, if this converges as a sequence. So that's our definition for when a series converges. And if it does converge, we declare that the value of the series is the limit of the partial sums. if a series converges, you have to have the terms in the sequence going to 0. That's what this basic necessary condition says. And you learn this in calculus, that if a series converges, then the terms go to 0. So why is this? Well, if the series converges, then the limit of partial sums equals some number L. And here's the n plus first partial sum subtracted from the nth partial sum. These both have to tend to L, but this difference is the n plus first term of the sequence. So this tends to L minus L, which is 0. So the terms tend to 0. But of course, this basic necessary condition is not sufficient, because as you learn in Calc 2 or somewhere, that the harmonic series has terms going to 0, but the sum is still infinite. Nevertheless, this basic necessary condition is actually quite useful when studying power series, because the basic necessary condition is almost sufficient when looking at power series in a certain sense. So next, let's look at the most important example of a series, which is geometric series. So consider the series from n equals 0 to infinity of z to the n, and I claim this converges and equals 1 over 1 minus z for z is less than 1 in modulus, and it diverges otherwise. So why is that? Well, the partial sums look like this. So it's just the sum of 1 plus z up to z to the n. And familiar formulas tell you that this is equal to 1 minus z to the n plus 1 over 1 minus z, at least when z is not equal to 1. If z is equal to 1, then you're just adding up n plus 1 ones. And we can examine when this converges. Well, for z less than 1 in modulus, the z to the n plus 1s go to 0, which means the series indeed converges to 1 over 1 minus z. For z equals 1, the sum clearly diverges in a precise sense to infinity. And I'm not talking about infinity in CP1 now, I'm talking about infinity in the extended real sense. But in all other cases, the series diverges because the terms are not going to 0. Now let's review a little bit about completeness. To talk about completeness, I need to talk about Cauchy sequences. And again, this is review from real analysis, where we're not using too much complex structure here. You can really think of this as living in R2. So if I have a sequence of complex numbers, it's called a Cauchy sequence if they all kind of cluster together far enough out in the sequence. So for every epsilon, there exists a natural number such that an and am are close for n and m past this big N. So if you go far enough out, they all start clustering. And we need Cauchy sequences to define completeness. So the real numbers are built exactly to have the property that it's complete. And you learn in real analysis, the real numbers and R2 are complete, which exactly means Cauchy sequences converge. And since we're using the same notion of convergence in C as in R2, the complex numbers are complete. The main way we'll be using completeness is to talk about absolutely convergent series. So we're going to talk about this basic fact that absolutely convergent series converge. I always thought this was such a silly thing to talk about when I was a calculus student, but it's more of a problem of terminology. Absolutely convergent initially doesn't have to mean convergence, but it ends up being equivalent to completeness, the fact that an absolutely convergent series will converge. So let me review what that even means. So if I have a series, I'll say that it converges absolutely if the sum of the moduli is less than infinity. And it's much easier to talk about a sum of positive numbers because the only way for it to diverge is for it to go to infinity. Recall that this sum here is finite if and only if its tails tend to 0. This is basically just a consequence of the fact that the partial sums increase to the limit of the series. Now let's prove what I was talking about a moment ago, that the completeness of the complex numbers automatically tells us that absolutely convergent series converge in the partial sum sense. So here's a proposition: absolutely convergent series of complex numbers converge in the complex numbers. So suppose we have an absolutely convergent series of complex numbers. Let's define Sn to be the partial sums. And we're going to show the partial sums converge, but we don't have that much to work with, so we have to use completeness of the complex numbers. So this can seem a little circular, but we're using the fact that the complex numbers are complete, and that's baked into how you build the real numbers. So in any case, if you look at the difference between two partial sums where m is bigger than n, you get this sum from n plus 1 to m of the terms of the series. And you can bound this by using the triangle inequality and putting absolute values in. And you can take this even further and send m to infinity in the sum. And this tends to 0 as n goes to infinity. So you can take your pairs m and n always, you take n as the smaller one and you send n to infinity. And this proves that the sequence of partial sums is Cauchy and hence has to be convergent by the completeness of the real numbers. Okay, but why is this useful? Well, it tells us that certain series converge without having to know exactly what they converge to. And that'll be useful on the next slide when we look at power series.